Usually, when we talk about advanced high-level mathematics, there's this expectation that we're just walking into a thick fog of Greek letters.
Right, yeah. Endless equations.
Exactly. Complex jargon, the kind of stuff that just makes your eyes glaze over completely. You expect a really dry textbook.
Oh, absolutely. It usually feels less like an adventure and more like, well, a punishment.
Yeah.
We tend to think of math as just a cold, rigid system of rules you have to memorize, not a way to actually explore the world.
But what if we told you that every great math problem is actually like a treasure hunt?
I love that framing.
Right. So today, you and I are hunting an invisible suspect, and its name is zero. We are doing a deep dive into this fascinating slide deck called 8.nonlineartechniques.pdf.
And it has this great subtitle, The Quest for Zero.
It does. And setting the stage here with slide 0, the premise is framing math as a hunt. But our mission today is very specific. We are going to use the Feynman technique.
Yes, the ultimate test of true understanding.
Exactly. We're going to take these incredibly complex, high-level concepts from the source material and translate them so vividly that you could explain them to a 12-year-old.
And have them completely understand the mechanics. Because if you can't explain the mechanisms simply, you don't actually get it.
Exactly.
Giving math a narrative purpose, like a physical treasure hunt, it completely changes how you approach the problem.
So let's start with section 1, the basics of the hunt. Because before you start looking, you need to know exactly what you are looking for.
Right, you have to define the goal.
And slide 1 characterizes the problem with this foundational mathematical expression. It's written as f of x star equals 0.
Yeah, f of x star equals 0. So to translate that from math speak into our 12-year-old's treasure hunt, that specific input, the x star, that is our exact spot.
It's the buried treasure.
Exactly. And the output of 0. Think of 0 simply as sea level.
Okay, so the analogy here is like you've just fired a rocket over the ocean, and you need to find the precise, exact spot where that rocket finally hits the water.
Right, because water is 0. It's sea level.
And this isn't just some fun theoretical game, right?
Oh, not at all. This is the exact logic used by aerospace engineers.
Wow, really?
Yeah, when they're calculating the precise trajectory of a spacecraft re-entering the Earth's atmosphere, they are searching for that 0.
The exact moment it hits the atmosphere.
Exactly. They are finding the exact moment the trajectory intersects with that invisible boundary. If they miss that exact spot, that X star, the spacecraft either bounces off the atmosphere like a skipping stone, or, it burns up by coming in too steep.
So finding 0 is quite literally a matter of survival.
It absolutely is.
Okay, so we know what we're looking for, the rocket hitting the water.
Yeah.
But how do we actually find that exact spot when we're staring at a massive mathematical landscape?
Well, slide 2 gives us our first tool. It's built on a concept called continuity and bisection.
And the math here, the formula, is x mid equals a plus b, all divided by 2. It's incredibly simple.
It is. You're just taking 2 points, adding them together, and dividing by 2 to find the exact middle.
So you're just chopping your search area in half.
Exactly. It's the safest, most foolproof method possible.
So for our 12-year-old explorer, the analogy here is the higher or lower guessing game, using fences.
I love the fences analogy.
Right. So imagine you have a massive, miles-wide field. You could put up a left fence and a right fence, and you know for a fact the treasure is somewhere between them.
Right. The treasure's trap.
So you just walk halfway between the fences to the exact midpoint. And you basically ask your compass, is the treasure to my left or my right?
And if it's to the right?
You pick up the left fence, carry it to where you're standing, and put it down. Boom. Your search area is permanently cut in half.
And you just keep doing that.
Yeah, you keep trapping the treasure by moving the fences halfway closer every single time.
It is incredibly reliable because if the landscape is continuous, meaning there are no sudden cliffs or teleporting gaps, you are mathematically guaranteed to trap the target eventually.
And there's a real-world application for this too, right?
Oh, absolutely. This is the exact logic behind binary search in computer science. Think about how a computer searches through a sorted list of like a billion contacts to find your specific friend's name.
It doesn't just read them one by one.
Right, that would take forever. It jumps to the exact middle of the list, asks, is the name I'm looking for higher or lower alphabetically, and then throws away the wrong half.
That's amazing.
Because of the power of exponential halving, a computer can find one specific name out of a billion in fewer than 30 guesses using this bisection method.
Okay, wait. Moving fences is safe, and 30 steps is lightning fast for a computer. But if I'm a human out in the field hunting treasure, Doing that manually just sounds, it sounds incredibly slow.
Like moving at a turtle's pace.
Yeah. So what if our 12-year-old asks how to speed it up? Because safety is great, but sometimes you need the math to automate the heavy lifting.
Well, that pushes us into section 2, speeding things up. You start with brute force, and then you look for elegance.
Okay.
Slide 3 introduces techniques that use the landscape itself to go faster, starting with fixed point iteration.
Right, and looking at the formula for this one, it's x sub n plus 1 equals g of x sub nn, which essentially means your next step is just a mathematical transformation of your current step.
Exactly.
And the analogy the notes provide is the magic boomerang, where you throw out a guess, the math transforms it, and hands you back a slightly better guess.
Right.
But I'll be honest, that feels a little like magic. What is the actual mechanism there?
Let's make it a bit more functional. Instead of a boomerang, think of it like a sourdish starter or feedback loop.
Oh, okay.
You take today's output, your current best guess, and you feed it right back into the machine as tomorrow's input. The function processes it and spits out a new number.
And then you just do it again.
Yeah, you take that new number, feed it right back into the exact same starting slot, and run it again. If the math is structured correctly, the changes get smaller and smaller with every loop.
Until it just stops changing.
Exactly. It settles. That moment it stops changing completely is called the fixed point.
So you're creating a circular dependency on purpose and just waiting for it to stabilize.
You are. And the most famous real-world application of this is actually Google's search algorithm, PageRank.
Wait, really? Google uses this?
Yeah. When you search for something, how does Google know which web page is the most important? Well, they decided a web page is important if a lot of other important pages link to it.
But wait, that's a chicken and egg problem. How do you know if the linking pages are important unless you've already ranked them?
Exactly. It's completely circular. So Google uses fixed point iteration. They assign every page a random, totally guessed rank.
Just a total guess.
Yep. They feed those guesses into their giant mathematical machine, which calculates a slightly better rank based on the links. Then they take those new ranks and feed them right back into the start.
And they just loop it.
Millions of times a second. Until the numbers finally stabilize and stop changing, they find the fixed point and boom, that's the search result you see on your screen.
That is genuinely fascinating. A feedback loop that resolves its own circular logic.
It's brilliant.
But let's say we don't want to loop endlessly waiting for things to settle. Slide 4 brings us to a major upgrade. Newton's method.
Ah, yes. This is where we stop walking blindly and start using the geometry of the land to our advantage.
The formula here looks a bit intimidating. It's x sub n plus 1 equals x sub n minus f of x sub n divided by the derivative f prime of x sub n.
Right, but physically, it's just describing a relationship between your current height and the steepness of the ground beneath your feet.
And the analogy here is brilliant. You are riding a skateboard down a massive, smooth hill, trying to find the absolute bottom, the zero. But instead of riding all the way down, you have a laser pointer.
Yeah.
You aim the laser straight down the slope of the hill you're currently standing on, and you look at exactly where that laser dot hits the flat ground far away.
And that dot is your next guess.
Exactly. You just skip the whole ride.
And we should explain why that works mathematically. The formula tells you to take your current height and divide it by the slope, the steepness.
Right.
If you are really high up, but the slope is incredibly steep, the math knows the bottom isn't far away horizontally, so the laser point's relatively close.
That makes sense.
But if the slope is very shallow, almost flat, the math knows you have a long way to go, so the laser projects much further out.
So you are literally using the angle of the hill to predict where the hill ends. It's basically a geographical shortcut.
It is, and it's incredibly fast. This geometric shortcut is actually how the GPS system in your phone works.
Oh, wow.
Yeah, when your phone gets signals from satellites, intersecting multiple 3D spheres is highly nonlinear. So your phone's processor uses Newton's method.
It uses the laser.
Exactly. It makes a rough guess of where you are, calculates the slopes and angles of the satellite signals at that exact spot, and projects a mathematical laser to a much better guess. It does this in milliseconds to lock in your exact coordinates.
Okay, so Newton's laser is incredibly powerful. But looking at the mechanics of it, it requires you to know the exact steepness of the hill at every single point.
The exact derivative, yes.
What if our 12-year-old explorer forgot to bring their perfect laser steepness meter? Or what if the landscape is too bumpy to get a clean reading?
That is a very practical hurdle. Finding that perfect derivative is sometimes mathematically impossible. Which leads us to slide 5 and the Secant method.
And looking at the notes, The equation here looks like absolute alphabet soup. It's just fractions and previous steps and subtractions. What is this actually doing physically?
Strip away the symbols. It's just replacing the perfect laser with a manual calculation. It calculates the steepness by looking at the past.
So the analogy here is the trail tracker.
Right.
You don't have a steepness meter. So instead, you just stop, look back behind you, and draw a straight line through your last 2 footprints.
Exactly. You calculate the slope between where you were a minute ago and where you are right now.
Then you just project that line forward and follow where it points.
Yeah.
So it's practically as fast as Newton's laser, but it only relies on your own recent history.
You're deriving the trend from your own data. This is heavily used in weather forecasting, actually.
Oh, because they don't have perfect equations for the whole atmosphere.
Exactly. Meteorologists use the temperature and pressure from yesterday and today, their last 2 footprints, to calculate the rate of change. They draw a line through those 2 data points to predict tomorrow.
That is so cool.
Yeah.
Okay, so moving to section 3, creating the ultimate tool belt. Our student has a bunch of tools now. They have bisection fences, which are safe but slow.
Right.
They have the Newton laser, which is lightning fast but needs a perfect slope. And the Secant trail tracker, which is fast but needs past steps. How do they choose?
Well, in the real world of engineering, you almost never choose just one. Slide 6 introduces hybrid techniques. You combine them to cover each other's weaknesses.
So combining bisection with Secant or Newton,
Mm-hmm.
safe combined with fast.
Exactly.
And the analogy here is so vivid. It's like you're wearing a jetpack, but you're also wearing a parachute.
It's the ultimate fail-safe protocol.
Yeah.
You want the incredible speed of Newton's method, the jetpack. You want to skip the journey, but sometimes the mathematical landscape gets weird.
Like the slope flattens out unexpectedly.
Right, and if you fire the jetpack on a weird slope, the math projects your laser point thousands of miles in the wrong direction. You fly wildly out of bounds.
You get blasted into outer space instead of finding the ocean.
Precisely. So what do the algorithms do? The moment the fast math detects that it's being thrown out of bounds, it instantly deploys the parachute.
Oh, wow.
It completely abandons the jetpack and falls back on the slow, reliable bisection method. It slowly drifts you back into the correct area using those safe left and right fences.
And then once you are safely back on a predictable slope,
You fire up the jetpack again.
that is amazing. And that sounds exactly like the logic used in self-driving cars.
It's exactly the same logic.
Because autonomous vehicles have to use lightning-fast predictive math, the jetpack, to steer in milliseconds. But if that fast math gets confused by a shadow, they can't just guess wildly.
They'd crash.
Right.
Right.
They have a slow, safe, unbreakable mathematical backup role of the parachute to ensure they just break safely.
Speed when you can, absolute safety when you must.
Which brings us to slide 7, the single variable tool belt summary,
Mm-hmm.
our explorer's backpack.
Right, let's review it.
Bisection is the slow, reliable turtle. Fixed point is the steady runner. Newton's is the fast rocket. Second is the race car. And the hybrid is the unbreakable tool, the rocket, plus the parachute.
It's a complete arsenal.
But hold on, let's really push the boundaries here. Because everything we just talked about, moving fences, drawing lines, that is all happening on a flat plane.
It's all two-dimensional.
Yeah, you're just moving forward or backward. But what happens in section 4 when our 12-year-old looks around and realizes the real world is 3D?
This is where the training wheels come off. Slide 8 introduces multivariable problems.
And the notation changes. It's a capital F with a little arrow over it equals a 0 with a little arrow. Vectors.
Yes, which just means we are dealing with multiple directions and multiple variables at the exact same time.
So the analogy upgrades to the 3D treasure map. You aren't just looking north and south anymore.
Right, you need east and west and up and down. You're trying to find the single spot where multiple, completely different landscapes all hit sea level at the exact same synchronized moment.
And the real-world application here is like programming a robotic arm.
Exactly. To make a robot hand smoothly grab a cup, you have to calculate the exact synchronized angles for the shoulder motor, the elbow motor, and the wrist motor simultaneously.
Because every joint impacts the others.
Exactly. They all must reach their collective zero at the exact same time.
So how do we actually find that 3D zero? Slide 9 brings back Newton's method, but multivariable. And the star of this calculation is the Jacobian matrix.
The Jacobian is the beating heart of multivariable calculus.
Okay, to explain this to our 12-year-old, we use the analogy of a 3D slope compass.
I like this one.
Imagine you are no longer on a simple 2D ski slope. You are now standing on the side of a massive 3D mountain valley, a giant gravity bowl.
Right, because in a 3D bowl, you could step north, south, east, west, or anywhere in between. And the steepness changes depending on which way you face.
So the Jacobian isn't just a single slope. It is a magic compass that physically feels the steepness of the terrain in every single possible direction around you, all at once.
Yes, it processes all of those different slopes instantly and points a single arrow straight down the absolute steepest path into the bottom of the valley.
That is incredible.
And aerospace engineers rely heavily on the Jacobian when designing airplane wings.
Oh, because of airflow.
Exactly. Air doesn't just hit the wing from the front, it flows over it from every possible 3D angle. The Jacobian helps computers find the precise wing shape that minimizes drag across all those dimensions at once.
But wait, I have a question here. Moving into section 5, shortcuts and hidden dangers. If this magic compass has to literally calculate the exact steepness in every single direction before it takes a single step, wouldn't that take massive amounts of computer energy?
You've hit on the exact bottleneck that limits modern computing.
Yes, I knew it.
Calculating a perfect Jacobian is incredibly computationally heavy. For complex systems, it would take a supercomputer years to calculate the perfect slopes for just one step.
Wow. So what do they do?
Slide 10 introduces the quasi-Newton and Broyden methods, which is basically mathematical shortcuts.
So you're approximating the Jacobian, trading perfection for battery life.
Exactly. You swap out the perfect magic compass for a guesstimate compass.
So instead of meticulously measuring every exact slope before every step, you just start walking.
Right. You guess the slope based on how your feet feel as they hit the ground, and you just update your map on the fly.
You save massive amounts of energy.
And this specific shortcut is exactly how artificial intelligence is trained today.
Wait, really? AI uses this?
Yeah. An AI neural network doesn't just have 3 variables like a robotic arm. It has billions of variables.
Yeah.
Calculating perfect slopes for all of them using a true Jacobian is practically impossible. The computers would melt.
So they guesstimate the slopes.
Exactly. They use these quasi-Newton shortcuts to train the AI in weeks instead of centuries.
Okay, so we've hacked the compass. We have an amazing tool belt. But slide 11 brings up a terrifying thought. What if the problem isn't the tools? What if the problem is the mountain itself?
This is a concept called conditioning. It addresses the fundamental nature of the landscape.
And the formula here looks at the absolute value of the derivative at the root. But the analogy for the 12-year-old is the difference between the steep cliff and the flat beach.
It's a great visual.
Imagine you're looking for the exact millimeter where the water meets the land. On a steep, rocky cliff that plunges straight into the ocean, finding the waterline is incredibly easy.
Right, because the slope at the root is incredibly steep. That's a well-conditioned problem. A sharp, unmistakable 0.
But what if you were on a flat beach? An ill-conditioned problem.
Right.
If you were on a muddy, perfectly flat beach, finding the exact millimeter where the water officially starts is almost impossible. The landscape is too shallow to read.
Is the edge here, or is it an inch to the left?
Exactly. A tiny breeze completely moves the boundary. Even the best math tools in the world will fail if the landscape is that flat.
And this has massive implications in architecture. Engineers have to ensure they are designing buildings based on well-conditioned mathematical models.
Because if they use a flat beach problem,
Their math is overly sensitive. A tiny, unpredictable shift in wind speed could cause a massive mathematical error in their load calculations, and the roof could collapse. They need a steep cliff of certainty.
which brings us to slide 12, the Master Explorer, and the ultimate takeaway of this entire Feynman mission. Looking at all these sources, the message is clear. Math isn't about memorizing numbers.
No, it's about choosing the right tool to discover the invisible truths of the universe.
The equations are just the physical tools in your backpack.
They are the compass, the parachute, the footprints.
Think about the incredible toolkit we've unpacked today. We started with moving fences to safely trap a treasure. We learned how to track footprints in the mud when our lasers broke.
We strapped on jetpacks and parachutes so we could fly fast but never crash.
And we stepped into the 3D world using gravity bowls and guesstimate compasses. It's just an incredible journey.
It's a brilliant testament to human ingenuity. But, if we pull back from the math for a second, I think there is a broader, more philosophical application here.
Oh, I like where this is going.
Today, we hunted for mathematical zero. But think about the concept of zero in your own messy, non-mathematical life.
Applying the toolkit to reality.
Exactly. If all these advanced tools exist just to find the point of perfect equilibrium, what is the zero you are trying to navigate toward today?
That's a great question.
And more importantly, are you using the right tool to find it? Are you stubbornly moving fences when you should be looking back at your own footprints? Or are you flying blindly with a jetpack, assuming the landscape is perfectly smooth, when you really need to deploy a parachute?
That is absolutely something to chew on. Your life isn't a textbook, and it rarely gives you perfect formulas. It's a muddy 3D landscape. Make sure you've packed the right tool belt for the terrain.
Well said.
Thank you for joining us on this deep dive. We hope you keep exploring, keep questioning, and keep hunting for your own invisible truths. Catch you on the next one.